section 4, but section 4 is just going to be this lecture, and it's going to be on non-abelian quantum Hall states. I'll explain what I mean by non-abelian. And what we're going to see is this word non-abelian refers to the anyons in the system. So the anyons are going to have more interesting structure than we saw before. So again, like everything in condensed matter physics, the theorists don't get anywhere. It's experiments that really drive them. It's really shocking how true this has been until the last decade. And so the experimental result for this is the following statement. There is a very clear plateau. So by plateau I mean a quantum Hall state.
Can I just say one thing about that? Shouldn't the model we draw from this be that the theorists in condensed matter physics should just take the opposite view, explore the landscape of all theories, and just propose they're all realized? I don't know how useful that is, but
I think there's some. I just pointed out yet again experimental theories.
These are words that are very heartwarming, but this is not what flies with my experimental projects.
I know, but they're just too conservative. Look at the data.
There are these more avant-garde theoretical condensed matter. Xiaogang, like Sophia.
So I think it's okay if this style is done by the very top people in a few places, but if most of us start working like this, I think it's like this is how it should be.
So the experimental result is a quantum Hall plateau at filling fraction by halves. So Gautam asked for a quick summary of what I did in the last lecture. And in the last lecture we went through what's called the hierarchy construction, or the Jane construction. They're two slightly complementary pictures, which shows you how you get other filling fractions, how you build other filling fractions, starting from the Laughlin state, in some sense, and thinking about deformations of that. So, most of it won't be necessary. In what follows, there'll be one point in the talk where maybe I'll do something else.
So it's composites and composites of composites and that kind of...
So there's two different approaches. One is that you start with a quantum Hall state. You look at the holes in the quantum Hall state, and then you think that the holes form their own quantum Hall state on top of the original quantum Hall state. And then you think that the holes in that form another quantum Hall state on top of that quantum Hall. So you start with this parent state, so you and then you form a Dawes state and a Dawes state, and they all have different fractions, and those fractions agree fairly well with what's seen. That was one approach. That's not quite Jane's approach, I should say. Jane's approach is a little more abstract. It's thinking about taking the electrons and attaching things called vortices to them, and these new objects and what he calls composite fermions.
And you explained it.
Yeah. No. I said some words. I don't know if I explained it, but I said some words. Okay, so the point is that all of these hierarchy constructions or Jane constructions, you always get filling fractions with an odd degree. And this has an even. So this is not going to be explained using the kind of techniques that we had in the last lecture. And in fact, what we'll see is that this has properties strikingly different from any of the other quantum constants. In some sense, much more interesting. Okay. So this has been seen. I think there's another one seen at 7 halves as well. And to my knowledge, they're the only two that are seen. Even fractions. Maybe there's a one. This is the one that's very, very clear.
And this is 5 halves with the Zeeman energy big enough that it's just single species?
No, so let me explain what 5 halves means. The electrons, of course, have spin up and spin down. And so far, we've just been talking about
one species.
One species. We've been neglecting spin. And the reason you can neglect spin is because there's a strong magnetic field, so that the spin up has a different energy from the spin down. Okay. In this case, what happens is, obviously, it's 2.5 Landau levels. The first Landau level, say, is all spin up. That's the lowest energy. The next Landau level is all spin down. And the final Landau level, it's now known experimentally, is all spin up, but only half. Okay. So that's the way this is 2.5. So if you like, you could think of it being 1.5 of spin up and 1 of spin down.
Okay.
So the first thing to notice is obviously it's also a higher Landau level. So until now, everything we've been discussing has been lowest Landau level, less than 1. And this is greater than 1. So you might think the way forward is to start thinking about what wave functions look like in a higher Landau level and working with those. And that's going to be difficult. It's going to be difficult because a lot of what we were doing was working with holomorphic. Like the lowest Landau levels, those wave functions are all holomorphic in Z plus the exponential piece. And that holomorphic sort of brought us a lot of restrictions, which meant in some cases there were only certain things we could write down. And we really don't want to lose that by working in a higher level. So what people actually do is make the following argument. All Landau levels are equivalent. In the sense there's a one-to-one map from one Landau level to another. We even wrote down this map in the first lecture. In the first lecture, when we were constructing Landau levels, I wrote down a creation operator, A dagger. And given a state in one Landau level, A dagger would give you another state in the Okay. So what people say is the following. Yes, we're in the second Landau levels of spin up, and there's some interactions between electrons. But you can recast that problem in the second Landau level.
And I'm really sorry,
yes.
I've forgotten by now, but so the problem, just to go back to your first lecture, the problem became that of basically a simple harmonic motion, and then is the lowest Landau level the lowest thing of the harmonic oscillator, and then
Exactly.
So then you can write down a dagger.
Yes. So what you do is you think about motion of electrons in this higher Landau level. You can do this for any Landau level, and they're interacting with some potential. And you can recast that problem purely in terms of the lowest Landau level, but where the potential gets modified. And you can do this very precisely. In fact, in the notes I explain how to do it. Precisely using these A's and E daggers. So the game people play is you don't write down wave functions at the highest Landau level. You yet again write down wave functions at the lowest Landau level. And the price you pay for doing that is that what was previously a Coulomb potential between these electrons becomes some modified potential down the low. Now, in some sense, that's no price to pay at all, because it's not as if solving the Schrodinger equation with a Coulomb energy. We're making stuff up. So we'll just continue to make stuff up. And, at the end of the day, there's some different.
But this transformation is really a proper canonical transformation.
Yeah, it's a genuine. Yeah. It's not a.
So if somebody wanted to do numerics with the wave function you propose, you would just use the other Hamiltonian.
It's this. This is the potential, and it's literally...
Right, so you would just choose another potential to do the numeric, if you want to.
Exactly. Yeah. Okay, so the upshot of this is that what we're after is actually to describe a Landau quantum Hall state at filling fraction a half. Because we can transform this to a lowest Landau. Okay, so the upshot of all of that is all Landau levels are equivalent. We look for a wave function. Now, something you missed out at. In the last lecture, we explained what happens at nu equals a half if you actually look in the experiment, actually at nu equals a half. And at nu equals a half, as opposed to pi halves, you don't see a Landau, you don't see a plateau. Instead, what you can show is that it's actually a Fermi surface. So it's quite remarkable, and I think it's sort of the crowning glory of James' approach. It's that in this composite fermion approach, you take the electrons, you couple these mysterious vortices to it. That's a composite fermion. And precisely at nu equals a half, you can argue that composite fermion doesn't experience a magnetic field. Which is very striking, because these are huge magnetic fields. And yet it agrees with experiments, so at nu equals a half, there's this sort of new emergent degree of freedom, which acts as if it doesn't feel a magnetic field, and it just piles up with water Fermi cells. So we saw that briefly in the last lecture. What this means is that actually we need to find a different state at nu equals a half. So we've already got one state, which is the Fermi surface. This is saying there should be a completely different state at nu equals a half, which is a quantum Hall state. And which one wins is going to be dictated by the interactions So the idea is there are two possibilities in U equals half. There's the Fermi surface state we saw in the last lecture. There's a new quantum Hall state, and both of those are possible, and which is actually realized in experiment will depend on the details of the interactions. We don't really have much control over. But experiment is telling us that when the interactions are pure Coulomb, it's the Fermi surface that wins, and when the interactions are Coulomb but modified by these lowest by the factor in a higher Lambda level, it's 5 halves. I don't think anybody has any real understanding of why this is true, other than numerically, but that's kind of the picture. Is that clear? Just kind of the motivation for what we're going to do.
Well, if you take this transformation, the green potential becomes A, V, A, dagger, then the stuff that had formed from its surface before, that may not even be around because you're doing different physics.
That's true. So you might think that the Jane's composite fermion approach was valid for one state and not for the other. Yes. Later in this lecture, we're going to see there's a beautiful connection between these two. So they are related, but they need, but it does tie together very much.
But it's not like the Jane's, the Fermi surface forming state. Yeah. You multiply that by A, and that becomes the...
No, it's much more physical. Yeah. And we'll, I don't want to spoil the surprise, so we'll see in 30 minutes or so how they're running. It's a beautiful thing. Other questions about... Okay, so this is our goal. Write down a wave function for electrons that are fermions that describes a quantum Hall fluid at filling fraction 1 equals a half. And there's a very, as we've seen, tried and tested way to solve problems like this, which is you just make stuff. So that's of course how this wave function was arrived at. So more, due to Moore and Reed, in what's surely one of the most important papers in all of quantum Hall physics, for various reasons. They do a lot in this paper. And roughly speaking, they guessed the wave function. Now it's not quite true. What they actually did in this paper was show that there's a deep connection between quantum Hall physics and conformal field theories. They showed that, which I'm hoping we'll explain in the last lectures of this course. They showed that all of the wave functions that were known for quantum Hall physics, Laughlin, hierarchy, various others I didn't mention, they could all be cast as correlation functions in particular conformal field theories. That's the first thing they showed in this paper. And so they didn't really guess a wave function. What they guessed was a different conformal field theory. And then from that, they wrote down a correlation function of a different conformal field theory, and they said, maybe this is the wave function that describes this. And it now looks as if this is the right case. So the wave function is very easy to write down. And it's the following. It's a lowest Landau level wave function. Remember that psi tilde means it's the wave function where I in order to write the exponential. Okay. So what I need to do is just explain what this symbol PF stands for. PF is the family. So PF is the Fathian, and let me just remind you or tell you what a Fathian is in case so I believe you have no idea. So just as an aside, so for any n by n anti-symmetric matrix, matrix Mij, and it's anti-symmetric, and I guess doesn't have determinant 0, the n should be even. Then the determinant of m is always a total sum. Which is a statement about linear algebra. and it's obviously everything's a total square, and essentially you can take the square root. What this means is the determinant of m will always be a square. The determinant of m is always a polynomial in the elements of m, but it will always be a square of another polynomial with integer coefficients. Okay? And that object, which is the square root of the determinant, is called the Pfaffian.
It's just you take the epsilon symbol and you just take A's and you contract it.
Exactly. So what does it mean in practice? It means formula. So here's two formulas. The first is that you just take the elements m12, m34, all the way up to n-1n. You multiply them together, and then you anti-symmetrize them all ways of taking this. In terms of what Sandy just said, more or less epsilon symbols. That's the same thing as doing the following. You sum over all sigma in the permutation with S of n, the sine of sigma, that's your epsilon symbol, times the product. M sigma to the 2k minus 1, k 1, okay. Alright, so here's two explicit formulae for it. Okay, so let's do our usual counting argument to think about what the filling fraction of this is. So remember, what you do is you look at the highest power of z's. The highest power of z's are for a single particle, the biggest ring of wave function that you get. That tells you the area of the droplet, how many states are in the droplet, and then you know how many electrons you get. That's the usual way. So the filling fraction. Highest power of z, a given z, z1 is m to the n-1, that's what you get from this Lofton-like piece. But then there's just going to be one power of z1 on the denominator. Right? Because you can see z1 only appears once in each of these, and then you're summing over things like this. So it's just minus 1. Which in the large limit is approximately n times n. Okay, so the same kind of arguments we had before tell us that the
M
is the thing up here in the
but you fix it eventually too.
Yeah. So the same arguments we had before tell us that the filling fraction of this is not affected by the Pfaffian. Okay, it's the same as in the Lofton case. But what the Pfaffian is doing for us is changing the statistics of the particles. Because this is anti-symmetric. So the whole wave function is anti-symmetric whenever m is even. And it's symmetric whenever m is odd. So psi tilde mr describes fermions. And even and bosons for m. Alright, which is the opposite from the Lofton state. So it means that m equals 2 is a candidate state.
So by this argument of zeros giving good energy and so on, this looks like you like them to come near each other now.
Sure,
The reverse of zeros, so is that attractive in fact?
This has a much more interesting structure. So suppose we take m equals 1, which is the smallest you can take, because this has a singularity. So you need the singularity to be cancelled by something. So the m equals 1 state nice, and everything else is just multiples.
But that's boson, right?
So it's boson.
Okay.
But this is where the essence is. So what happens? The Laughlin state had the property that it vanished whenever any two particles came together. This state, when m equals 1, has the property that it only vanishes if 3 or more particles come together. Okay, because if 2 particles come together, there's a 0 here that's precisely cancelled by a 0.
Yeah.
And only if 3 come together, you get an extra 0 here,
It's not good.
which is not. So it has this, this very nice structure that it's sort of 3 particles, and this generalizes. So there's things called Reed-Redz-Eye states, which are built on the idea that you should write down a wave function which only vanishes when p particles.
But when n is 2, what is the then?
So when n is 2, again when 2 particles come together, but that underlying structure of m equals 1 is still sort of the seed of this wave function. As for exactly which interactions prefer this, do you know, I think there is something you can say. Do you remember those pseudo potentials? And that you do the potential two-body.
Yes.
Potential.
That should get an attractive piece, right?
Yeah. So what? If you remember what happens, V of. So you have these angular momentum states,
Right.
and you had V of R, so they had some potential. This becomes approximately, the value of this is approximately V measured on R is the square root of 2m times m. Yeah. And you can show that what happens when you put the, if you have some repulsive potential like this, the eigenvalues are basically these discrete values. You can show that what happens when you go to higher Landau levels is it suppresses these, it suppresses the first few. These remain the same, but the first few get suppressed. So the interaction becomes weaker. And I think maybe you could imagine that it actually becomes attractive. I'm not sure if that happens. Perhaps. Okay. Good. So we've got a wave function that when n is equal to 2, looks like it might describe particles. And what we want to do is ask what are the properties of this quasi-constant. And in particular, what are the quasi-Hall and quasi-particle excitations. Are there any questions about this? Okay. So let's look at quasi-Halls. And again, we're just going to make stuff up. The question is, what's a wave function you can write down that naturally goes like that? So you could try the following wave function, just motivated by exactly the same ideas we had for Laughlin. So we just multiply by this usual quasi-Hall factor. This by all the same arguments, this looks like a depletion of charge, some amount in the region of eta, so it's a good candidate wave function. It turns out that there's something a little more subtle you can do here. That this is not the most elementary quantity. And the way to show this is just to write down what the answer is and then see how this emerges. So there's a way, there's a more subtle way. To introduce quasi-Halls. Which is the following wave function. And the subtlety is to make use of the fact that so instead we could write down a wave function where we put some quasi-Hall positions inside the vacuum. So what have I done? I've introduced two quasi-Hall positions, eta1 and eta2. The argument of the vacuum has to be antisymmetric. Pfaffian only makes sense for an antisymmetric matrix. So it's antisymmetric on the bottom, which means whatever's on the top has to be symmetric. So I had a Zi minus e to 1 and a Zj minus e to 2. And then I'm obliged to add the other term with Zj and Zi.
This allows you to introduce two quasi-holes, I guess.
It's two quasi-holes, except when e to 1 is equal to e to 2 is equal to eta, this gives back this.
Right, so it's actually half.
This gives the original guess. So this Pfaffian actually means that each of these sort of Loftin-like quasi-holes is able to itself split into two pieces. It suggests this by going into the Pfaffian where you have sort of a more general kind of wave function. So it's as if the Loftin quasi-hole, put that in inverted commas, meaning this thing on the left is split into two.
And we cannot do this for n holes.
We'll see when n holes is where all the interesting things happen. Yeah, but you can't split it more.
Oh,
Yeah, because it's just a true statement. You can't. Yeah, we'll see what happens with n hole, but it's this which turns into this. And if you put, say, 4 holes here, that would look like 2 holes. So each one gets to split into two. Okay. So in particular, if we knew from the Loftin argument that this has charge E over n, it strongly suggests that each of these guys, labeled by e to 1 and e to 2, has charge E over 2. And in fact, that turns out to be correct. It's worth mentioning that it predicts that the nu equals half state, that particles have charge E over 4, and this was seen experimentally maybe 5 years ago, fairly, maybe a little more, but fairly recent. It's a good sign that this is the right.
So this is at 5 halves.
That's at 5 halves. Yeah, equals 4 was seen at equals 5 halves.
Sorry, I'm confused. N for us is 2, right?
2, so 2 for nu.
Good. And then for 5 halves, that's what I understood. Because it's the half fill.
Yeah, so the other 2 lambda levels are just inert and aren't doing anything in terms of dynamics.
Okay. So in this lecture, when you're saying u equals to, you mean 5 halves translated into
Nu equals a half is half plus.
Yeah.
Yeah, plus integers.
So to check this, one could again do the charge density in eta 1, or the checkup is E over 2, and do some charge densities. How would you do that? I mean, earlier you said that one could compute this charge density around the board. I mean,
earlier we had a few ways. One was just to argue that if you put enough of them together in the wave function, they look like an electron. One was in terms of the plasma analogy, and the correct way was to do a buried phase type of calculation. All the last 2 of these you could do here, but it's much more complicated. And I'm going to mention it. We're going to talk about statistics now, so I'll sort of mention the way in which it's complicated. But I was just going to say, I think the simplest argument is that
2 of them make this.
Yeah, it's 2 of them make this, and you know that n of these make that.
Right. The fact that people enjoy these wave functions, they work so well. Let me ask this question again, if you don't mind. Could it be, and everyone's writing a bulk wave function, right? But could it be that the bulk is hardly important because you told me it's not the case, but let me ask again. Because all effects really come from the boundary. And in the boundary, there's something universal because the bulk is pure Chern-Simons and the boundary is the boundary of the. I mean, could it be like that? I mean, otherwise, how on earth? I mean, I don't know. This is
No, but Sandeep, the excitation is a bulk.
Is it?
Yes. The quasi-coil lives in the bulk.
But the
It can
boundary
be
knows
even
about it.
experimentally, you know that
The boundary you're talking about is when you can have excitation-less flows, which are just the boundary current,
But I think
without exciting.
Sandeep is asking experimentally, how do you see this? And it must be one boundary tunnel into another.
Yes.
We're not really sure
Yes.
if the bulk is, at least I'm not sure if the bulk is
Well,
playing a role or not. In principle, this is what people dream of. You should be able to do
Tunnel,
put these
yeah.
objects in the bulk and actually arrange
Yeah.
them, right? That's kind of the goal
Yeah,
of
okay.
Microsoft Station Q.
So I guess it's a different question whether experimentally what's being measured is in the bulk. But I think there's no doubt at all that these are bulk properties theoretically, and maybe people have only so far seen subtle tunneling signatures of that.
But what I mean is, if the bulk wave function is correct, then these are bulk properties, right? But the bulk wave function, who knows, is correct or not.
But it'll have the right universality.
No, but the point is it has the right kind of quasi-particle. I mean, this is this business of predicting what kind of structure of fractionalization you have.
But how do we know?
You're asking if the wave function is exactly this or something else with the same fractionalized quasi-particle.
No, I mean, even how do we know that it's the same, fractionalized quasi-particles if all the measurements are more edge
You
measurements?
can do numerics. That's always an option, and this again works very, very well.
Right, so I mean, whether the measurements can probe the bulk quasi-particle, yes, I agree that's a difficult. I think most of the signatures for this fractional stuff comes from some short noise which measures the overlaps and things like that, right? Is that bulk or boundary? That's boundary. There's no edge tunnel.
It's edge to edge,
Edge to
through
edge
the
through the fluid. So what they measure is the graininess of the current, short noise, and that just tells you whether the objects carrying charge or E or D or a fraction.
But to back up your claim, the way Moore and Reed got this was by computing around root correlation. You insert two extra objects, and then it appears here in the CFT. So the CFT knows about this. If you put things in the bulk, somehow the CFT. We'll get there.
Yeah, I know.
Totally positive about this,
But it's just
we'll get there in these lectures.
random subject.
Yeah, it's weird. It's weird. And hopefully when we get there, we'll have all the evidence in front of us and we can really try and understand.
Are you sort of saying that all bulk wave functions that are the same kind of fractionalized quasi-particles in the end have the same low energy boundary theory, and that's why that's the robust way to think?
That's
That's
a
true.
true statement. Yes.
That's what I'm trying to
That's
say.
true.
Yeah, that's a true statement. And sorry, no, go ahead. Here's the weird thing. I just don't get it at all. Laughlin guessed the wave function.
Yes.
Could have guessed one out of a billion different
Yes.
wave functions, but he
Picked the right
because it
one.
was easy to write down. Then when you go to the CFT picture, you compute a correlation function.
Yeah.
Why is that the same as the one he guessed?
Yeah.
I don't understand. It's probably to do with holomorphy, and once you've got that, there's not. From this matrix model, I gave a talk, you can write down other holomorphic wave functions in the same universality, but they don't arise as correlation. I don't understand. But we'll get there maybe in the lectures.
Wait,
Explain what's going on to
the
everybody
edge
else.
theory is a 1 plus 1 B theory, right? And that's the one that's kind of universal.
The boundary theory.
Yeah, that's the one, right? But these correlation functions are in some other thing, he'll tell us about. Is that right?
No, correlation functions are in the boundary edge theory.
And then there's a map that David's been emphasizing is totally mysterious between the boundary and the bulk, right?
So, as I understand it, the boundary theory is the theory of particles living on,
Yep,
let's say, a circle
living
by
on-
with quantum mechanics.
Yep.
So there's a tau,
That's right.
and there's a.
Yep.
Exactly.
But now you're going to take correlation functions in that space-time
Yep. It's the wrong space.
and map it to correlation functions in this two-dimensional
No,
bulk.
map is too strong. I'm
I
going to
see.
calculate them
Okay.
and notice that they're exactly the same
I
as
see.
the wave.
Okay.
Not me, I'm more on me. This is the
Okay.
deep idea of all this. Let's do your question. What happens with Morgan? This is where the meat is. This calculation is the reason Microsoft gave Leiter, gave millions of pounds to Santa Barbara Station. Shiraz, we should very quickly do a summary. We're trying to write down a wave function at filling fraction mu equals a half that is a quantum Hall state. Okay? So last week we said at mu equals a half there's a Fermi surface state. We don't want a different one at u equals a half, which is a quantum Hall state. And there's going to be two competing states, and dynamics is going to pick which one is going to choose. Okay. The reason for this is experiment. There is an experimental quantum Hall state at u equals 5 halves, which if you strip off 2 inner lambda locus is the same as u equals. So the wave function we wrote down is the more real wave function. Following, this is a Pfaffian. The filling fraction is 1 over m. M is this thing here. The difference is that now this obviously is antisymmetric, which means the whole wave function is antisymmetric when m is equal, as opposed to the Lofton state, which is antisymmetric when m is equal. Which means that m equals 2 is the same dimensions. So this is a candidate wave function to describe quantum Hall states. The next thing we noticed is that the quasi-holes are interesting. You could take this and multiply it by the factor that Lofton introduced for quasi-holes.
Same way.
Yes, exactly. But there's a more subtle way. Those quasi-holes can themselves split into 2. And this is the wave function that shows that. So this is a wave function for 2 quasi-Hall positions, then eta1 and eta2. It's symmetric above and asymmetric below. But when eta1 is equal to eta2, you can take the thing on the numerator and factor it outside, and you get back to the Lofton quasi-Hall wave function. So the Lofton quasi-Holes in this effort is split into 2 quasi-Holes, so their charge is a half that of the. And as you can see,
Lofton thing was Zi minus eta product over, right?
Yes. So now we're getting on to the most interesting case, which is what happens if you have 4 factors. And we'll see that there's a...
So you're interpreting this as the quasi-Hall is itself a bound state of 2 things?
I'm actually going to rename it. I'm going to call each of these a quasi-Hall.
Okay.
But bound sort of suggests there's some kind of dynamics. These things are free to move anywhere they like. If 2 of these quasi-Halls come together, let me call these more real quasi-Halls. 2 more real quasi-Halls come together, you get the Lofton kind of.
And it's the suggestion that even away from now filling the quasi-Halls you told us, but last time into more?
No, something very special about half. Okay, so what happens for 4 quasi-Halls? I'll just write down wave functions. So I'm going to introduce some new notation because you can see already the numerator is getting a little longer here. I'm going to introduce the mutation of psi tilde and then on the subscript open bracket 1, 2, open bracket 3. And this is going to be equal to the Pfaffian, open bracket 1, 2, open bracket 3, 4, times the product that's Pfaffian of power Z, times the Lofton-like product that's outside.
Sorry, could you say what the notation is? Span 1, 2,
Yes. Yeah, I'm going to write this down now. So I'm going to define what this Pfaffian means. So this Pfaffian is shorthand notation for the following: Zi minus eta1, Zi minus eta2, Zj minus eta3, Zj minus eta4, plus what happens if you exchange I? So the 1 and 2 means that Zi is matched with 1 and 2, and Zj is matched with 3. Okay, I should say what the motivation for this is. Again, there's a conformal field theory motivation that underlies it all. But what's really going on here is this is an element of the matrix. It's the ijth element of the matrix. And the natural thing to do is to make the ijth element of the matrix depend only on Zi and Zj. It's anti-symmetric on the bottom, which means whatever's on the top has to be symmetric. We've seen that quasi-Halls are things like Z minus etas. So this is naturally 4 quasi-Halls where Zi contracts with 2 of them and the other Zj contracts with 1. By the way, I should also say you can do what you did for Lofton. We didn't do it for Lofton, but you can write down toy Hamiltonians where more read is the ground state and these are the excited states. So you can play that game.
What is the degree of zero when I goes from J wave function? There's M and then there's something that's around.
I think I have a feeling it's when M is 2, I have a feeling that the abelian phase is an eighth. Do you know, I haven't found in the literature an easy computation of those. There's a long paper by Kitai from this one. But I think it's complicated.
What are you taking around what?
But much more subtle things happen than just getting effects, which is what we're thinking.
So are you taking eta 1 around eta 2?
Yeah.
That's what you meant?
Yes. I was asking a simple question. I was just asking you Z1 and Z2.
But Z1 and Z2 is...
Oh, sorry, Z1, Z2, sorry, I was talking about etas. In the original guy?
Here, if you take Z, you're saying Z1 and
Yeah,
isn't just symmetric? I mean,
I don't think it changes by a phase, because this is a sum of things like 1 over Z1.
and then you
Actually, for a vacuum.
I just want to know the degree of the zero. There's something to do with something.
So this is the definition of a vacuum. Okay. So you're going to take Z1 around Z2. This is going to pick up a phase. But all the other terms in this have M1 multiplied by 3 and 1 multiplied by else. So I'm not sure what happens to that. It looks like it doesn't pick up a phase.
because the numerator doesn't vanish when Z1 equals Z2. And the denominator has a degree 1, 0, and the ZH minus ZN to the power n, because n is 2.
This has so the number of power of. So what's the exact question?
What's the degree of the zero in 1 and 2?
When Z1
I think
comes
there are
to
different terms with different degrees.
The lowest degree.
The lowest degree is
It's down by 1.
It's down by 1.
I think so. Yeah.
So
it's 1.
the lowest degree is. Let's take n equals
Did
1.
that anybody or
Let's take n equals 1. There's one term that doesn't have a z1 minus z2.
In the denominator.
No,
Anywhere.
anywhere.
Anyway, good.
Because one z1 minus z2
It's
gets cancelled by
cancelled.
1.
Yeah.
So it's down by 1.
So it's down by
Yeah,
1. That's
right.
it. Yeah, so I thought for our case where n is 2, then it's degree 1.
Okay, good. Yes, sorry. No. So we're done.
So it's down by 1 independent of the total number of particles. That's why the density didn't change.
Yeah.
That's why the Field fraction didn't change.
All right. So
And then,
this.
sorry, just to understand. And then, of course, there's a very non-trivial question: what happens when you take eta 1 around eta 2?
That's where we
the
go.
fractional space.
That's where
So
we
that's
go.
going to be all it is.
Okay, and let me just understand the status of all these wave functions. Now, are these a basis for holomorphic functions?
I don't think so. So what do they be?
Then what? I mean, eventually that's what you want, right? Because you want to write down every possible state, you can write down the lowest lambda level. You want to write down every possible holomorphic.
Okay, you want to write down ground states with respect to particular Hamiltonians and particular excited states.
Only particular excited states.
You don't want to write down all of them because they're less interesting. Just write down the first few.
Right, so the idea is not that by putting arbitrary numbers of quasi-particles you get all the excited states.
And at some point you're going to bring down because you've got to find a number of electrons and you want to.
Right, but let's say up to that point.
Do you want to get all? No, I don't think they're all states.
So then what is the status? Why are we writing down particular wave functions?
So the claim is the following: that if you have, by the way, and you are just guessing.
No, you're guessing. But the claim is that these diagonalize Hamiltonian?
The first claim is that there is a Hamiltonian, a local Hamiltonian you can construct, where this is the ground, more read is the ground state, and these are the excited states.
And these are the excited states of the Hamiltonian.
Yes.
Okay.
Yes. So there is a
Hamiltonian. Which in the real system, these are near to the excited states.
That's not right. Yeah, exactly. Well, but better still, they capture the same universality of the excited states, which means that they're going to have the same statistics when you grade the
Same
anion.
charge.
That's really where we're going. This is thinking about properties of the anionic excitations. And these wave functions, a simple wave function that you can write down that are in the same, that have those same properties.
I got confused by something. Here we split each Laughlin possible into 2.
Yes.
And now we.
So now you've got two Laughlin quasi-holes, and so each of those has been split into 2, which is why you've got 3.
So sorry, there would be you would be able to give me, let's say, you'd be able to give me an example. It's not true that any antisymmetric holomorphic function of the zi's can be written as linear combinations of things.
I don't believe so. No, I might be wrong, but I don't know why that would be.
Because we sound like, I mean, let's say where m equals 2. I mean, it sounds like you're basically getting polynomials.
Yeah.
So since polynomials can produce antisymmetric polynomials, and since Taylor series expansion produces anything,
This is a basis.
you're not getting the most Taylor polynomial. Okay.
But our interest is going to lie in a few special states.
Okay.
All right. So here's a wave function for 4 quasi-poles. But it's very clear that it's not the only wave function I can write down. Because I made this arbitrary pairing where 1 and 2 went with I and 3 and 4 went with J. So I can very easily write down 2 further wave functions. Also 2 further. Which, can I write here?
For me, it's okay.
But it's the obvious things. It's where you just do the other pairs. You do 1, 3, and 2, 4. And you do 1, 4, and 2, 3.
So the quasi-poles come in pairs.
Yeah.
Are these states orthogonal to each other? States with 2 quasi-poles and 4 quasi-poles, are they orthogonal to each other using the usual Hilbert space model?
2 and 4 will be, and states with 2 will be approximately orthogonal as long as the positions are larger than the magnetic units. It's like a coherent state basis. Okay, so it looks as if something interesting has happened. That you put in 2 quasi-poles, and there's a unique state with 2 quasi-poles. Now you put in another 2, so you have 4, and suddenly it looks like we have a degeneracy emerging. It turns out that we do have a degeneracy, but the degeneracy isn't 3, as we've written down here, because these 3 states are not all linearly independent. So it turns out there's a relationship between them. And I'd rather not show it on the board. I did go through the derivation in the printed notes. It's a couple of pages and it's just linear algebra. But the claim is that the following relationship holds. The difference of 2 of these vacuums is equal to a difference of another 2 multiplied by some factor where eta alpha beta is eta alpha minus. Okay? So there's a little bit of linear algebra that you can do to show that there's a single linear relationship between these 3 states.
It is some kind of grade algebra that.
It's going to end up as a grade algebra, but at the moment it was just things that look a bit like conformal field theory. But remember it's just linear. So the upshot is that there's 2 states describing 4 quasi-poles.
Four quasi-poles and 4 given. Specify the locations.
Specify the locations, how many states are there? Those fixed positions. Of course, as you move them, you get them. Infinite number. Okay, so
had there been bosons, there would be just one state. If you specify the locations. Had there been identical particles, if you specify the locations, there would be one state. Or there's some.
Also, sorry, yes. If the quasi-poles had been bosons.
Yes.
Yeah, of course, right. This is the fact that these are some kind of anions, but these are not abelian anions. Okay. So this is, this algebra I could have done in 5 minutes. on the board. Let me now tell you the general claim. So the general claim is with two n possibles. The degeneracy is 2 to the n minus 1. Okay. Which I'm definitely not going to go on the board. It was proven in about 94 or 95 by Nyack and Wilczek. And again, it's just, it's easy to write down a whole bunch of quasi-Hall states by having lots of products in the numerator of the factor. And then it's sort of some fairly complicated linear algebra to figure out what the linear independent basis is. So it's conceptually straightforward, but it's kind of fiddly to actually. Okay, so is the statement. This is very strange. This is the first thing that I want to stress. The minus 1 is, I guess, marginally strange. We'll see where it comes from shortly. But the fact that it's n here in the exponent, not 2n, is really the thing to take. Suppose you had the following. Here's an easy way to get degeneracy of states. Each particle has spin up and spin down. Each particle has a two-dimensional Lorentz space. And then if you have a whole bunch of particles, 2n particles, the dimension of the Hilbert space is 2 to the 2n. Because each one can be up or down. This isn't this. So because the exponent is not equal to the number of particles, it means there's no way to think about these states as capturing information of a given particle. Okay? Instead, the state you're in is somehow subtly encoded between the correlations of all the possible particles. Right? Said another way, if I was to give you the wave function for any one of these states, but only allow you to look at that wave function in some local region, you've got no way to know which state it will be. All the states look same in any local region. It's only when you have the global structure of the state that you know what's going on.
Just for a sneak peek, there's going to be some Chern-Simons theory associated with this state, right?
Yeah, ultimately. Yeah.
But can you tell us the level and rank?
SU2 or level 2?
And these are going to be fundamental particles?
Mm-hmm. Do the fusion rules for fundamentals and okay. So the information about the state is a global property, not a local. Okay, what's more, we can do the following. We have these particles, and there's, you put 2n of them down, and there's a Hilbert space of this dimension. So they're in one state, this Hilbert space. And now you do grading. So now you take two particles, and you exchange them. So we've seen that previously you don't get bosons or fermions, you get anyons. But now you can get something much more interesting. Because you start in one state, you take two of these identical particles and exchange them, and you can end up in a different state in this Hilbert space. In other words, that when you swap particles, you don't get phases, you get unitary operators acting on this Hilbert space. That's sort of the big conceptual leap why these states are solved. So, grading of particles means that you get a non-abelian Berry phase which in this context means a unitary operator acting on this Hilbert space H, where the dimension of H is 2 to the n.
So maybe just more for the sneak peek, to get the 2 to the n minus 1, I just wrote down the character of this representation, this discrete character, raised it to the n minus 1.
Of the Cacciamuri algebra?
Of the Cacciamuri algebra. No, sorry, not the Cacciamuri algebra. Just this, SE2 character, but with eigenvalues restricted to the discrete values. Just raise it to the power 2n. I think that will be it.
Well, you can, but with level 2, the j's, we should not interrupt the lecture, but the j's are 0 and 1. right? Because it goes up to k over
No,
2.
0, half, and 1.
0, half, and 1.
Yeah.
Sorry, 0, half, and 1.
This is the half. These are the halves.
Okay.
Oh, so we don't get all the roots. We only get the halves.
No, he starts with the half.
Yeah, each particle is a half.
And now, maybe simple way.
Yes, so if you take the head without any holes, put it on a VSG guide,
Put it on a...
surface of VSG.
Yes.
What is the shape?
No, now it's there's an answer, and I can tell you where to find it, but I've been unable to find the time to go through the derivation. It's a long answer. So the question was, if I was to take this state, put it on a Riemann surface of genus G, what's the degeneracy? The answer was first figured out by Reed and someone who I can't remember. There's even a paper by Nyack and company which is called something like Topological Order for Idiots. They use a beautiful argument of Sentil about how you can calculate this degeneracy, but it turns out that there's all sorts of subtleties. So, I understood the first 15 pages, and then the subtleties just piled up, and they get the answer. So it's out there in the literature, but it's not easy to.
But it's number of possible states when you put the
number of ground states when you put this theory on it.
Oh, when you put this quantum polygon.
You could work it out from Chern-Simons.
Yes.
The math between this and Chern-Simons is not so strong. Yeah, and the fusion rules are clear, but there are more subtleties there.
It's not just the degeneracy of states for Chern-Simons or something.
Yeah, it is, but there's discrete identifications, and then there are again subtleties. Okay, so why is this important? This is why Bill Gates is giving billions, maybe hundreds of millions to this fact, to Station Q, and why lots and lots of people are excited about this. Okay? It's the following: you've got a Hilbert space. When you put in a bunch of these particles, you've got a Hilbert space, but the Hilbert space is a global property of this system. In particular, if you knock the system a little bit locally, a cosmic ray comes in and hits it, or you blow on it, or I don't know what these people do, but if you have any little local disturbance, it can't affect this Hilbert space because it's capturing global properties. What's more, if you want to do, if you do this braiding, so you exchange this around, so you shuffle these particles around in different ways, you start to build unitary operators on this Hilbert space. Now, a unitary operator acting on state is exactly what you need to build a computer. You need a whole series of unitary operators. So the idea is, and this is an idea, very famous paper due to Kitaev in the late 90s, that this is the way you build fault-tolerant quantum computers. Where fault-tolerant here is one of the key ideas in quantum computing. It means that you're immune to errors. You're immune to errors due to decoherence with the environment, or small little phase shifts, or spin flips. Because all of those errors are induced locally, but there's nothing local about these states. These states are captured by global topological factors. So that's the dream. The dream is that you can use these systems to build quantum computers that are immune to effects. Anyway, that's it. In the notes I have a section called "There is a subject called Topological Quantum Computing," where I say that. But there are books written. And in particular, beautiful lectures by John Harris.
This correspondence between, this Williams-Jones polynomial paper, the correspondence between Chern-Simons and Wechsler
Yes.
at the boundary. That's already doing that sort of thing, right? You do stuff in the mouth.
That's exactly it.
So he should pay millions to, they already solved the problem.
The difference is that he's having experiments. That's really why Bill Gates cares.
And since we are mapping this question to Chern-Simons and so on, if you don't mind, later maybe in the lecture, also can you map it to the toric code, to a particular toric code and the degeneracy in that toric code?
That's another example of this, but I don't think it's
not quite the same.
That's a Z2 gauge theory.
Or it can be Zn or non-abelian also. I could tell you all that. But
I don't know much about it. I view them as kind of in the same class of interesting objects, but I think they're different examples, although maybe there's a more direct relationship.
It's just because I at least understand the toric code and how to compute some of the degeneracies there.
So the next thing we need to do is to figure out what this braiding is, right? So I told you that if I take two particles and I exchange them, there's going to be a unitary map on the Hilbert space. And I'm going to work out what that is. If I exchange two particles, how do these states transform into each other? Okay, that's the goal. Any questions? Okay, so how would we work out this braiding? The obvious way to proceed is to do what we did before. We computed the Berry phase of the abelian annuals by just taking the wave function, differentiating it with respect to the phase, taking the overlap with the wave function. The standard thing you can do exactly that for these more read states. Right? Except it's hard. If you remember, it was hard for the Laughlin wave functions, and we had to resort to this beautiful plasma analogy with clever ways to do it. Here, it's much harder because there's no obvious plasma analogy. So it's been done. The story is that Gouari and Nyack made an attempt in the mid-90s to do this and suggested some kind of non-abelian version of the plasma analogy. And they couldn't push it forward, but about 5 years ago, Bonderson, Gouari and Nyack managed to complete this and cooked up some new plasma analogy and determined the braiding directly from the wave function. It's a very impressive paper. It's 80 pages long. It's very, very detailed.
I think I got that due to the end as well.
It's a very hard, I think, from my perspective, very difficult, very technically challenging. There's an easy way to do it. So the easy way was going before. So what I'm going to teach you here is the easy way to compute this braiding. The easy way also has lots of beautiful physics, at least in the starting. So I'm going to tell you this easy. Okay, so. The easy way involves something called Majorana zeros. And while the calculation is going to be straightforward, to get to the starting point of the calculation is going to require some physics, which I'm not that familiar with. So let me tell you where we are.
Yeah, sure, yeah.
It was also at 10
It was at 10, yeah.
It's good. We've been talking about Moore read states.
Mm-hmm.
So I've written down the Moore read state and written down the quasi-holes for the Moore read state and stated the fact that if you have two n quasi-holes in the Moore read state, there's not a unique state, but the number of states is 2 to the n minus 2. Okay. And the next step we want to do is understand the braiding properties of this. Meaning if you swap two of them around, now you get a unitary operator acting on this Hilbert space. And we want to understand the map between the choice of braid, swap around, and the unitary operator.
So in the physical Hilbert space of the problem,
Yes.
I will always have an even number of these particles, these Moore read particles.
Yes. You can't write down the wave function with an
Right.
operator. There might be something you can do with putting things at infinity.
I see. Yeah, okay, yeah, sure. Yeah.
From the conformal field theory perspective, they're to do with what's called twist operators.
At the bounding, yeah, sure. That's good.
Okay. So, yes, please.
Say, one more thing that's bothering me is the whole state you wrote down works for n even.
Yeah.
I mean, what's the deal with that? That can't be a physical fact, right? That it only works for n even.
Why?
So which state?
The Moore
The
state.
Pfaffian itself makes sense only if you have an even number of
No, sorry, even number of electrons.
Yeah.
Yeah, you need an even number of electrons.
Oh.
Yeah, sure. That cannot be a physical fact. Right? The state only exists for even
Well,
number.
that's true. And again, there must be sort of one that hides off infinity if you have a number.
No, but even if you write down a standard superconducting wave function, trial wave function for superconducting, you write it for an even number of electrons because they have to pair. And if you, in principle, have an odd number of electrons, that's going to cause a quasi-particle excitation over them. And in fact, if you make a really tiny superconducting blob, you will see this fact. You will see an odd even effect. Like Kushan saw it, I think, 20 years ago.
Yeah.
That's
So you're saying that if there's an odd number of electrons, there will be 2m quasi-holes.
I mean, superconductivity is suppressed if there's an, if you make these nano things, then it actually matters.
1 in 10 to the power 23 doesn't matter.
Yeah, but 1 in 1,000 or 10,000 will matter.
This fact is going to be very relevant, what I'm about to say. So I'm going to do this calculation using Majorana zero roots. The calculation will be easy, but to get to the starting point of the calculation requires some explanation. And I don't understand where everything I'm about to say comes from. But I'll tell you some facts, and then we can build off those.
In Chern-Simons language, it's a question of you start with a conformal block, then you take one particle around another, and see what the transformation is.
Yes, although I'll explain later. It turns out that it's more than that. That's kind of what people use, but there's assumptions in that about the map between Chern-Simons and quantum Hall that it is not true, though it's conjecture. I'll explain that later.
Okay. But the quantity I just mentioned is well known in Chern-Simons.
Yes, absolutely. Yeah. And we're going to match. In this case, it turns out it does agree with. Okay, so some statements. The more read state involves the fact. And it only holds for an even number of electrons. The first statement is something which Kedar just alluded to. This is actually the real space wave function for a superconductor. Apparently, a fact first shown by Dyson back in the 50s or 60s.
Really? You take the BCS wave function? So you just take states near the Fermi surface, and what's going on? Is that right?
No, I think
There's no Fermi surface here?
No, it's
we'll see where the Fermi surface comes from. Yeah. So this is just a statement that if you take a BCS wave function and write it in real space, it's a fact.
2D BCS.
Presumably.
Spinless.
Spinless, P-wave, in fact.
P-wave.
P-wave. Okay. So what does this have to do with anything? So now we match these ideas that we had in the last lecture. We've got two states at u equals a half. Okay, there's this Jane type state, which comes from composite fermions, which build up to give a Fermi surface. And now we've got this new quantum Hall state. And the, I think, quite lovely fact is that the two are connected. If you start with a Jane state, which is a Fermi surface, and those fermions undergo a Cooper pairing and condense to form a superconductor, what you end up with is the fact. So this quantum Hall state should be thought of as a superconducting state of composite fermions.
So whether you get this or that dependent interactions.
Yes. And in the lowest Landau level, the interactions are such that you get a Fermi surface. And in the 5/2 Landau level, the interactions are still Coulomb, but affected a little bit by the fact you're at a higher Landau level, and now these things condense together. So the more read state can be thought of as a Fermi surface of composite fermions with pair to form a superconductor. So this idea was floating around in the 90s for a long time. There's lots of papers, Greiter, Wen, and Wilczek. Even the original Moore Reed paper makes some reference to this. It was finally shown with some level of precision by Green and Reed about 2001. So it's a very technical paper, but they really show exactly how this arises by starting with the Jane-like composite Fermi on the Fermi surface and looking at the interaction and seeing it. Okay, so that's a nice statement. The next statement is the following. The quasi-Hall states we've been looking at arise in this picture as vortices. Vortices in the superconductor. And I should mention that the kind of superconductor you get is a type of P-wave superconductor, is what's called PX plus IP. And the final fact that I need is that each vortex carries a single Majorana zero.
On the state is the same thing as a superconductor.
Yeah.
For these composite fermions, which are not real electrons.
But I see. But I thought superconductor. I see.
They're gapped.
Yeah.
Right? That's the first defining feature.
And they would conduct, but not electron charge, but quasi-pole charge.
I don't quite know how they're conducting.
Well, the composite fermions are dipoles.
Both of them have rho xx equals 0. Right? That's the definition of a superconductor and a quantum core.
It's sexy. But if I did it the other way.
Okay, well, I'm going to do it. But the point is, it's all about rho xy, right? You can believe that attaching these fluxes to the electrons gives some non-trivial rho xy. I don't know how it works.
Also, it's a px plus ipy.
It's px plus ipy.
So it's got an angular momentum in the condensate. Condensate carries an angular
unit angle.
That's the key thing.
It has to by symmetry because the composite fermions are fermions, and if it was S-wave, you would have anti-symmetry in the spin, but you don't have spin anymore to give the anti-symmetry, so it has to carry.
But can we turn on a gauge field for this? I mean, can we make this superconductor really? Can we set up
Flow.
superconducting current? This thing? No, because there's nothing to couple it to. Why not? If it's a superconductor, why can't I look at the state where it's got a non-discrete current?
So he's asking where is the persistent current of the superconductor?
Statement is that the composite fermions that we are talking about, I think, are they don't have electric charge; they have electric dipole.
Okay,
so the current you will get is the current of particles that have a dipole moment, but not a charge.
Okay, but there are many states in the theory.
Yes.
Different states. They're long-lived. They live forever.
Yeah.
Maybe they don't carry electric current. They carry something.
In many states,
Suppose I've got a superconducting ring. Maybe I say it's wrong. Sorry. I thought you could set up a persistent current.
but that's not the. I mean, that costs kinetic energy.
It costs
That
energy.
got energy half rho s js square.
Costs energy. But this is a state that will live forever.
Yes.
So there should be such a state in the.
He's asking what is the equivalent of that here.
It's certainly not electric current flowing. It's
Sure, but something's happening and lives forever. Some conserved something.
I mean, let me try to ask the question to combine a little differently, which is topological states are mysterious because we don't have conventional order parameters. The superconducting states are, in that sense, easier.
Yeah, but
So what is the order parameter?
the order parameter is a composite fermion, which if you write it in terms of has that flux attachment is a non-local property, so this also doesn't have a local.
Yeah.
It looks local, order parameter is a very non-local object.
Because superconductors are easier on that count, right? And then the currents and all are tied to that, right? So is there a way to understand it through symmetries and by breaking, more conventional scripture? So px plus ip by these kind of guys have some
That we are
kinds of order parameters, maybe carrying angular momentum 1, but that require expectation.
So in the composite fermion, which you can do that, it's not a local order parameter.
So it doesn't couple to a local
And there are-
probe of some.
And there are order parameters for the Chern-Simons spheres, the off-diagonal long-range one, which I think is also what they provide out of superconductors. But the problem is that they're not local. It's what people were using in the 80s. It's probably not right. Think about it.
So somehow there are no local probes that can actually couple to composite fermions, but somehow the rho xy still shows. You can understand the rho xy in terms of that's ultimately a response to some local probe, right? That's what I have never really understood why suddenly. I understand in the composite fermion picture that everything is, the objects are non-local in terms of original electrons. So if you couple things to.
I thought what was being done was to take the electrons and somehow say that the ambient flux is bunched up so that two vertices are on each of the electrons.
What's flux? What magnetic field?
Magnetic
Definitely.
field.
I think it's when Jane first.
No, it's not a magnetic field.
It's
Right?
not a magnetic
It's a zero in the way.
Yeah.
So, but wait,
So we often talk about flux attachment.
but hang on, you
If
counted.
there's a flux, it's the emergent Chern-Simons gauge field.
You see, but I thought the reason why we understood that it was a fractional filling was that we took the flux and some of it we attached to the
No,
electron.
that was a very
If by flux you mean magnetic flux,
Mhm.
this is the way it's sometimes explained in the literature, and it's just wrong.
I guess this is a question of whether you're doing.
Magnetic flux isn't a dynamical thing, right? It's under your control, and you've made it homogeneous and uniform, and there's nothing that.
I know, but I just thought what they were saying was, okay, we are going to work in some other approximation where the flux got punched up.
No.
This is
This
the flux
is
of
just
the
wrong.
transit.
I think
What
This is
punched up
written
is
on
this
literature, it's just-
fake gauge field flux.
yes,
In
the
the
emergent
Chern-
Chern-Simons flux being attached.
And even that you then smear out in some field approximation to look at.
Well, we don't need to go
Okay.
there. We'll see the Chern-Simons field. in 2
But
weeks' time.
David, if I took what you did last time, with these two zeros,
Sorry, why?
sorry,
Well, because I thought the point about the zi minus zj to the q
Yeah.
was that we took the square and we said, okay, we will somehow account for that locally.
But I never used the word flux anywhere in the last lecture. But, I talked about vortices, and vortices being phases of a wave function. That's the right way to think about it from the wave function.
so
And when we get to a Chern-Simons picture, it'll be emergent. The vortices will correspond to emergent Chern-Simons flux. But the magnetic field is always homogeneous.
So I thought the vortex, physically those were magnetic field vortices.
No.
We were computing statistics partly by taking things around. I was thinking of those as
no, Sandeep, that's the question of whether you interpret that statistical phase as Q star times B or Q times B star. Right? I mean,
star being the
you only
statistical-
you measure one thing, but
Well, you were worried because B star was lower than B.
Yeah.
Is that where that?
yeah.
Then finally, at the end of the day, it was like filled Landau levels,
Yeah.
right? Well, then filled with respect to which magnetic field, I thought, because
With respect to the composite fermions experience a reduced magnetic field. That's interesting.
I see. And why is it that it's a reduced magnetic field if it wasn't the original magnetic field that in some approximation?
Because all they really see is Q star times E star times B star. So I could have equally well said that they already have a smaller charge and a half filling. The reason that it's a free fermion is these composite fermions have effectively zero charge rather than see effectively zero magnetic. Because all you're really computing is the Aronoff fermion.
E times B.
Right.
And so all along, I thought that it was the magnetic field that's being reduced. But you say the correct thing is that it's the
I think it's the electric
It's all just
charge.
words, right? So it's you can say anything.
No, but it's not just words because of
But
what
the magnetic field is not bunching. That's important. It's always
Actually, magnetic field is not bunching. But I mean, what are the words that are justifying any of this? Okay, I should stop.
One way to say it is that these composite fermions are charged under two things: actual electromagnetism and the Chern-Simons.
yes, exactly.
So there's around like pi fundamentals, and they see the phase.
Which we'll see when we do the Chern-Simons.
At the level of whether they have the same charge and see a different magnetic field, a reduced magnetic field, or they have a different charge and they see the same magnetic field. It's correct that QB star is the same as Q star, but this business of whether they carry a charge or not should be a real statement for the, as he said, for the supercarrier part.
Yeah,
But ultimately, we're trying to explain why the state has a particular fraction with respect to the external magnetic field, right?
Yeah.
So there is some connection then.
Yeah.
If you cook up a Chern-Simons, then you have to ask why is that magnetic field
Yeah.
at all related to the external?
Yeah. So no, I'm not talking.
all of these questions we'll answer when we see Chern-Simons.
Okay,
These
so
are very
I
clear.
guess I didn't understand what was that.
But at the level of the wave function, you just showed that the product of the effective Q and the effective B they see is reduced, right? and you've not yet committed yourself to one interpretation or the other, whether the charge is reduced or the...
In fact, people jump around. As you said, there becomes another interpretation where the composite fermions
are
neutral,
dipoles,
but
right?
they become dipoles.
Right.
Which I mentioned.
Is that the real, real in the sense, if I make I mean, he seems to be sort of bringing up this valid point, right? If it's a superconductor, the superconductor.
Yeah.
If they carry charge, then that would be electrically
Maybe
charged.
that's the...
So it must be a dipole. The correct interpretation is presumably that the charge is reduced. And that's why the net Aharonov-Bohm's flux seen at universe R is zero.
You know, the problem with this is that you can't do calculations to test one or the other. Right? It's all very hand-wavy and intuitive.
Whether they have charge or not, must have operational signal.
Here's something else I'm confused with. Is you could start with this Halper and Lee-Reed theory, which is the theory for the Fermi surface, Chern-Simons theorem, and see things condense and hope that you get the effective field theory from Law-Reed, which is an SU2 Chern-Simons. I don't know how that happens. I've never seen that running in literature. Maybe it's my ignorance. That's not obvious.
So there's a BCS-type mechanism that's happening for the composite fermions.
Yes.
And what's the interaction between them? I mean, these are some two-dimensional fellows. So what plays the role of the...
Whatever the Coulomb interaction is, and dressed if they're in higher Landau levels, it gets mediated by the factor in higher Landau levels.
So it's always there. That interaction is always there. You know? Or why isn't the super pairing always happening?
I think it only happens at suitably low temperatures and I don't know is the answer. I don't know if it's thought that if you really reduce the temperature at rooms a half, you'll eventually see this.
It's the whole question of whether the effective interaction at the Fermi surface is attractive or not.
Yeah, so I thought that the phonon mediation...
You have matrix elements in wave functions and so on, so it's not just 1 over R. In this case, it's some way more complicated stuff. Somehow your Landau level wave functions will come into
What is it
picture.
appear because of the phase transition? The phase transition breaks the symmetry.
Or there are just fluctuations even at lower
Usually, okay, so I was thinking about cosmic strings. Usually people compare these with cosmic strings. What is this superconductors are same thing as cosmic string, the phase transition which go symmetry. So is there something like similar that you compare?
Phase transition as you vary temperature.
The phase transition in the universe are doing
As you vary which parameter?
very temperature. The superconductor also do very temperature. You have
Of course, you hit the
phase
superconducting
transition,
state of
then
low temperatures.
You see if you go from low to high, I think. Oh no, high to low.
high to low.
High to low.
So high state has this symmetry. The field is zero. Low state is
So that's the question. Yeah, if you have a Fermi surface at nu equals a half, it's really nu equals a half, lower the temperature, do you think you'll end up with a quantum state? And I don't know the answer. I don't think there's any experimental evidence.
But is there some phase transition interpretation for the quantum world?
No, they're in one's at nu equals a half, one's at nu equals 5.
Two different things.
And there are different filling fractions. You can both think of them as nu equals a half, but with different interactions between them. So it's not like you can vary from one to the other.
Ordinary superconducting quasi-particles above the superconducting state are going to be identified with these funny anions.
No, vortices of the positors.
Not at all.
There must be neutral excitation.
What are the quasi-particles?
Yeah.
What are the quasi-particles there in this picture? There's some neutral excitation of the Hopfield state.
I don't know. It was only it was only a couple of years ago that people actually managed to write down the wave functions for quasi-particles in the models. Because in the Loftus state they have derivatives and they're much harder to work with. But yeah, I don't know. See? Really? Only my ignorance, not the general field. Yes.
So just to understand, so maybe the right way to think about Jain's approach is, from maybe one perspective, is that you want to explain everything in terms of the integer quantum Hall effect. And then what you do is you take non-interacting electrons, but you couple them to the ambient magnetic field and the extra Chern-Simons gauge field which you cook up. Is that one way? And then you endow the level of the Chern-Simons and so on as you like, so that things work out right.
We'll derive Chern-Simons from a much more simple approach in the next lectures after this, and we'll see exactly how it connects with J. So roughly this is right, but we'll just forget everything we've done. We'll start from afresh, and we'll see all these things emerging from these perspectives, rather than trying to make the connection. Okay, so let's do this calculation because it's quite straightforward. So the claim is that the quasi-Hall vortices are once more in this particular setup.
The calculation is take one vortex from
exactly. The vortices come with a zero mode, which is a Maillard.
So we should take one around one or one around a bunch of others.
We'll do everything. So let's let me explain what a Majorana zero mode is. Okay, so usually if you have fermion creation and annihilation operators.
This is some matrix in conformity theory. What is the name? The matrix for
which is the
brains.
Sorry, the statement that the quasi-Halls are vortices in the superconductor.
Now, all of these are four facts which I cannot. Probably this one.
So this one is, so you write down this Topological design equation, right? This is 2 by 2 kind of Schrodinger equation for the quasi-quantum. In the presence of a background which comes from the vortex for a P plus IP superconductor. Because it's P plus IP, there is a variation of the phase of delta.
This is the way you find the zero mode. Why is the quasi-Hall vortex to begin with?
No. So I'm just saying why there is always a Majorana mode inside the. So then you can solve that problem and you can see that there's going to be a kind of a guaranteed zero energy solution to that equation, which is like this domain wall zero energy.
For a real superconductor with a vertex or whatever I can see.
No, so usually real superconductors don't have guaranteed zero modes. Only when the symmetry is px plus ipy, then they do.
For a superconductor of px plus ipy, where the problem, I can see how you would do it. My question more was in this context. Why is that true?
There must be a simple answer.
Why are quasi-Halls in a quantum hall like vortices? It's not a disappear.
Okay, so what do we usually have? If you have a fermionic creation annihilation operator.
Wait, so then where does the statement that the state is a superconductor come from? That comes from looking at the wave function and noticing what eigenvalue is.
These are four facts that I don't get.
That's this Pfaffian is the wave function.
Okay, so these are the usual fermion. Gamma rai is the same as gamma rai dagger. It's very strange, right? If C dagger I is a state that creates an is an operator that creates an electron in some state I, then this creates or kills an electron, which means that this operator doesn't conserve charge, right? C dagger should add charge 1, C should remove charge 1. So it's very unusual to be able to write down something physical where this makes sense at all, because charge is not conserved. This is, we know electric charge is conserved. In fact, charge is conserved mod 2, because this only changes the charge by 2. But that's exactly what happens in a superconductor, because charge is screened mod 2 in a superconductor. So in a superconductor, you have a hope that maybe this kind of thing makes sense. So given this, it's simple to show that these obey the following algebra, which is something that we've all seen before. This is a Clifford algebra. And that's going to be important. Okay, so for us we have two end vortices, which means that this label I is going to go from 1 to 2. Okay. So each vortex.
Just to understand, so if you expand your electron wave function in the background of this vortex,
Yeah.
you find one mode whose coefficient obeys the equation gamma square is equal to 1. And then
Find one real solution of the Topological equation exactly at zero energy.
exactly zero energy, and the
That's
coefficient
why
of
it's
that
real.
solution,
That's why it's real. It's a
the
real
coefficient of that solution when you canonically quantize
is exactly this.
yeah,
The point is it's a real solution because it's tied to zero energy.
Yeah, there must
And
be a
therefore
C,
it's-
C dagger.
Therefore it's C equals C dagger.
and the quantization tells you that this c squared is equal to 1 or 2 or 1. C squared is equal to 1, and then of course everything else is
Yeah. Actually, more precisely, if you put it on a circle and put the vortex in the middle, you get two. One living on the circle at infinity and one.
that makes no
Yeah.
So
That's what it
let's see what's going on here. If you have a single vortex with a single, actually, let me back up. Suppose you have one fermion creation and annihilation. Okay, well, what do you get from that? You get two states. You have a ground state which is annihilated by C, the next state which is where you hit it with C dagger, but you can't hit it with another C dagger because C is aggressive.
Yeah.
Okay? So one complex guy C gives you two states. What does one Majorana fermion do? It doesn't give you anything at all. Okay, so one Majorana fermion is just not a useful thing.
What does that mean? What's the Hilbert space for this algebra of gamma square is equal to 1?
It's got to come in pairs.
Yeah.
So physically what's going on is something is sitting.
So yeah, so if you can actually explicitly do this for the single vortex in the middle, and you will find one zero mode living in the middle, localized, and the other one localized on the circle, and together they are one C.
But as we've seen, our wave function only
Yeah.
makes sense when it comes to this.
Yeah.
Right.
So once you have two Majorana
So
zeros,
just to say, there's no one-dimensional Hilbert space implementation of
A single of a single.
Oh, wait.
No,
But just gamma is one.
gamma is-
I mean, it would be root two dimensional, right? That
so
is
you know, there are Clifford algebras in all
Yeah,
dimensions.
yeah. So gamma is one is just an implementation of the algebra in one dimension.
Must be. But I think it's not physically right.
No, but it's
It is, right? Because with one gamma, it squares to one
Yeah.
identity. And then, of course, that.
Yeah.
just that is one. Yeah.
So then one is always an.
Still, for us, we only ever have even numbers.
Fine. Fine.
So, but in a normal Topological transformation, if you have some Ci plus Ci dagger kind of thing, then there is an independent Topological combination, maybe Ci minus Ci dagger or something like that. That's what you get, right? I mean, if you start with some psi and psi dagger, you solve the Topological equation, then you get eta and eta dagger. In this particular case,
Gautam,
what's
that's
special
only
about-
if it's non-zero energy.
This is
You
what's
get two
special about
independent
this
things
case.
only if it's non-zero energy. If it's zero energy, then there's only one solution. That's the point.
I mean, other way of thinking about it is
I see.
UV and minus U star V star. So you
That's
can
one.
arrange them so that they're all the same. Which doesn't mean degenerate, which in this sense means that's why solutions of the BDG equation that have energy tied to zero are special.
If you just look up free Majorana fermion in a circle with periodic boundary conditions, you'll have a zero mode which has gamma 0 square is equal to 1.
This Majorana is different from particle physics.
Yes, yeah, they should be given different names. Yeah, they both obey something like this, but they have different kind of physics. Okay, so how do you build the Hilbert space for this if you've got an even number of these guys? Well, what you do is you arbitrarily pair them up. So you take gamma 1 and gamma 2, and you define something which is gamma 1 plus I gamma 2. And then you get gamma 3 and gamma 4 and pair those up. The way in which you pair them up is completely arbitrary. These then obey the kind of things that we started with in this sense.
So in particular, this means that two Majorana modes will give you one two-dimensional Hilbert space, right?
Exactly, yes.
But what we had was two polygons giving us a one-dimensional.
We'll see this, yeah. We'll see that factor of two dimensions. The key thing is though that if you have two vortices here, you have a two-dimensional Hilbert space, but it's not that you can associate that to either of these two. It's a property of the two of them, not a property of any single. That's the globalness that we saw earlier. Okay, so you build the Hilbert space. Well, how do you do it? You just insist that the annihilation operators kill the vacuum, and then you just hit with creation operators. So what do you get? You get 0, side dagger i's, acting on the vacuum, side dagger I, side dagger j, acting on the vacuum, all the way up to side 1 dagger, side 2n dagger, acting on the vacuum. Sorry, not 2n. Half as many sides as you have.
So you will get 2 to the power n.
Yes, exactly. Good.
Like in the Ramon sector.
Yes, exactly. Yeah. Which means the dimension is 2 to the power n, which is 2 to the n minus 1 times 2 to the n minus 1. Okay. Which, as you pointed out, is twice as many as
dimension. Wait.
What is that?
1 cent times 2.
Sorry. Okay.
Plus?
Plus?
Yeah.
It's certainly true.
Okay.
So you have to remove one factor.
All right. So there's something here that I don't understand, but it's my lack of understanding, no one else's. Obviously, it's a factor of 2 too big.
Yeah.
We will see that this Hilbert space and this Hilbert space don't mix with each other. So that if you sit in a state in this Hilbert space and you do the grading, you stay in this Hilbert space. And the same for this one. So let me see what I mean by this.
The 2 are when you have odd or even number
Yeah,
of
exactly.
side
Even number of side daggers.
I know that. Okay.
So all numbers.
Okay. So the exact chiral and anti-chiral? Chiral spin and anti-chiral spin.
It's exactly that, yeah. That's
What is chiral?
Okay. So imagine this is a gamma algebra.
It's like 3-dimensional gamma, which is the same as the 2-dimensional.
We'll see this. These two
Oh,
Hilbert
right.
spaces.
Okay, I see. But just minus 1 to the f.
Exactly, yeah.
Yeah.
But probably it will also.
If you think of the one that is the triple algebra and the chiral spin algebra.
Okay, so the Faffian wave function, the Faffian quasi-holes that we saw, are 1/2 of them. So the question I don't know the answer to is what's the physical interpretation of the other half? Someone asked what are the quasi-particles in this, and it may be that the quasi-particles in the other half. But, I'm embarrassed that I don't know the answer to this.
Sorry, Faffian.
So we wrote down the Faffian wave functions.
Oh, one.
Quasi-holes, the number of them I didn't prove, but claimed was equal to 1/2, equal to this. And so there's a natural way to split this Hilbert space and say the even or the odds.
So you have these psi particles and you are saying break it up into even number of psi particles and odd number of psi particles. And all the quasi-hole states are the even number or whichever. Right? Is that because we needed 2 to get the Lofler?
There's 2n in each case. The question is, what's the dimension of the Hilbert space given these 2n quasi-holes or 2n vortices? Twice as big for the vortices with Majorana rows, but the Hilbert space decomposes into 2.
And only one part of it.
So I don't know why there's this minus 1 to the f projections. Maybe you should only consider 1/2, or maybe the other half has a natural interpretation.
So let me just to go back, just the preferred algebra has. So if it's really true that these Majorana modes can be thought of as C plus C dagger, then you do get 4 states, right? That is forgetting about just forgetting about the quasi-particles. It seems, at least if the map of quasi-particles to Majorana, quasi-holes to vertices and vortices to single Majorana 0 modes is correct, then doesn't just the problem with the single Majorana mode suggest that we have some express.
You see some projection.
I can understand. So I mean, if the yes, I think you're right. The the vortices and Majorana modes suggest that you have this number.
This number, regardless of quasi-particles, I'm just saying.
Yeah, but the Pfaffian quasi-Hall wave functions have this one. So maybe you need a projection. Maybe these have some physical interpretation.
So I don't know if this has bearing, but in the Kitaev honeycomb model, which is a spin model, you can rewrite it in terms of Majorana exactly like this. And given some boundary conditions for the spin model, the Hilbert space of the spin model is exactly half the Hilbert space of the Majoranas, and it's exactly this kind of half, even number of particles in any channel. And so that's because there is a projection to get the spins from the Majorana.
But if there's a projection, where is it coming in the physics in this map?
So that's the map you didn't tell us.
Maybe buried in there is a projection.
Because this is exactly what happens in the Kitaev honeycomb model when you write down when you write down the spin Hilbert space, you must take half the Majorana Hilbert space corresponding to definite parent.
It's clearly the option for projection. I just like to know why physically that projection is there or if it's not. Alright, so given this map, we can now think about the braiding.
Is SO2n going to play any role in it?
Yeah, that's exactly right. So let's introduce the operator.
This is GSO prediction.
What's that?
This is GSO prediction. So in the world shape theory, we say that it comes from modular.
So what would GSO do given the Fermi surface? So Ri exchanges Ri is going to be an operator which exchanges the I and I plus 1 vortex. So you have a bunch of vortices. 1, 2, 3, 4, and this exchange is going to happen in an anti-clockwise direction. Which means and so what we need to know is what such an exchange does to the Majorana. And I'll give you the answer, which looks reasonable to me, and I couldn't fully I couldn't derive it. So it seems reasonable. By the way, this whole calculation is due to a guy called Ivanov in about 2001. And it was the first time there was a very, very simple calculation to explain these grades. Before then it was quite a lot of complicated. So the grading on the Majorana modes is going to be the gamma I turns into gamma I plus 1. That makes sense because we're swapping them. Gamma I plus 1 turns into minus gamma I. So this is the slightly subtle minus. And gamma j just goes to gamma j, j is either of the culprits that get exchanged.
You mean you want a unitary matrix that will implement?
We'll write down this eventually.
U gamma U inverse should have the same.
It's a SO2 rotation.
So it looks, you might wonder why a gamma I plus 1 and gamma I have been treated differently, and I think the answer ultimately is that they're fermions.
Yeah, there's this minus sign also in more inside.
Must be because this is all.
Yeah.
That was sort of the first place.
Yeah. You know, if you take in conformal field theory, if you take one operator completely round the other, that's basically an R-round home phase. If you do half of exchange, then that's the R-round home phase square root, then there's a minus. Then you could abstract the form there.
Okay, so we want to represent this as a unitary operator. As you said, you called that unitary operator U, which is maybe more sensible because I'm conflating notation, but I'm going to call the unitary operator Ri. And the Ri that does this, it's very easy to check, is e to the pi over 4 gamma I plus 1 gamma I times by some arbitrary abelian phase that isn't fixed. So this abelian phase is the kind of thing we took care of computing for Loftin anions. In this Majorana approach, you don't get to fix the abelian phase. To see that, you have to go back to the original wave functions or do something more specific.
So the square of this is what takes 3 out of 2?
Yeah.
So this is like the square root of the Arno-Bohm phase.
Yeah. And if you expand this out, it turns out it's, if you actually want to do the calculation of it.
Square root. So it's not a B-matrix. So
Yes, matrix with spinorial representation is not.
So if you do if you expand it out, because these obey the Clifford algebra, it turns out that it might just as well. The square root of 2 comes because the sine of pi over 4 and cos of pi over 4 is square root of 2, minus square root of 2. Yeah, that's right. Yeah, there's a factor, string factor of 2. Yeah. And then the states get mapped to by the same unitary operator.
This is taking care of the delta function.
Yes, this is exactly the same as that. So there's a little bit of algebra you need to do to convince yourself that's true, but it's interesting. So in the notes I went through and just did a few simple examples. What happens if you have 2 quasi-holes? Okay, there's a phase which is undetermined. What happens if you have 4 quasi-holes? 4 quasi-holes, you start to see the non-abelian nature where you get more than a phase, that the states start transforming into each other. Let me just say, and it's been pointed out already, you've seen this before. Okay, this is just SON group theory and the spinor representation of SON. So let me just make that connection manifest.
SO2.
SO2. Thank you. Yeah. So we've seen this before. And so if I introduce the more general brain matrix Rij, which swaps I from J vortices, then what I've written on the board there is the same as writing Rij to be minus I pi over 2. There's your factor of 2, Sandy. It's slightly surprising. Tij with Tij being pi over 4 gamma I gamma j, which is precisely the spinor representation.
I mean, it's just like that 90-degree rotation, that's what you want, right? It's gamma 1 to gamma 2.
Yeah, but since you're flipping the numerator, it's a
you do. In this abstract space, you do quarter rotation, not half rotation. It's slightly unusual. And acting on the 2 to the n-1 Hilbert space, well, that's just divided by the chiral spin. Just to state that there's a gamma 5 which can project, which commutes with this. Okay, so now you have something very explicit. Now if you braid any of these quasi-holes, you can see exactly how you move in the Hilbert space. And you move in some interesting non-abelian ways. Things get transformed into each other by these unitary properties. Yes?
Like, you can raise 2n and not n.
Because the Clifford algebra was made up of 12 things.
Where do I, okay, what sign here?
Where ij goes from 1 to n. No, sorry, ij goes from 1 to 2n.
Right.
Oh, okay, then.
Yeah. Where's n? There's no n's.
No, 2n. 2n.
I thought there were n.
No, it's 2n. And then you made those n complex fermions to create the Hilbert space. Alright, so this is the simplest example of a non-abelian quantum Hall state. And you can see that there's much more interesting physics than
So this braiding just interchanged I and J.
Yes.
And if you do it twice, it'll take, let's say, I around J.
Yes.
But if you want to take I around a bunch of other things, how do you do that?
You can generate the entire braid group just from the things that I called RIs. I exchanged with I plus 1. So you just do this consecutively. These have to obey some Yang-Baxter equation, which
And so in this case, it's very simple because it's just rotations which you identify and you think.
Okay, so this is the
But do you do it just geometrically by, I mean, you want to go from one configuration to another and you just think abstractly in terms of the exchanges that get you there, but the order matters, I guess, etc.
you have to put an arbitrary order in to begin with, but the labels you added.
Oh, and then the Yang axis tells you that in the end it doesn't matter. It doesn't matter. That's
Yes, okay.
okay. Yeah, now I realize. So you just do it.
Okay, so we can see that things start to get a little more complicated. This is the simplest example of a non-abelian quantum Hall state. So what do? We wrote down wave functions. We were able to determine the linearly independent wave functions. See, it's possible to determine the linearly independent wave functions. It's possible to compute this braiding using the Berry phase of those wave functions, although it's very hard. There's this other nice map to just Majorana modes, and you can determine it this way. And then always at the back here, as we'll see, is some conformal field theory. So it's possible to map this to conformal field theory and determine the gradient. So everything fits together very, very nicely. For other non-abelian quantum Hall states, as far as I can tell, you're in a much worse situation. So typically, the only handle you have is this conformal field theory. The wave functions are too complicated to figure out which one's linearly independent, how the Berry phase works. There's not a nice map, as far as I'm aware of, to things like Majorana modes.
So once I know that there are Majorana modes sitting in the middle caused by creating some object, the rest of this is independent of where that came from?
Yeah.
That just follows.
Yeah. So if you have another system with Majorana modes, this is
exactly what
the
we
brain.
have.
Yeah. Yeah, it's very nice.
Something I'm not get reached to the. If we thought that the probability theory we had two operators, we took one around the other. How it would phase would depend on what these two operators fuse to.
Yes.
Now these two operators could fuse because they're halves. They could fuse to either 0 or 1.
Yes.
So we should get two different eigenvalues depending on the details of the state. I'm not saying
Only the zeros.
The one could combine with other stuff to make a singlet.
How many quasi-holes in total?
2. I just
Then one of them could
combine with whatever.
combine with one that came from another two fusing together.
Right. So it should be that there are two different. If I take this operation and square it, it should be that matrix has two separate. Oh, and this is the plus minus. Thank you. That's just the plus minus.
The two sectors.
No, not the two sectors. It's a pi rotation.
Yeah.
I was just thinking this matrix should have two different eigenvalues. One corresponding to the 0 and the other corresponding to the 1. And that's true.
These are two-dimensional matrix.
I suppose it's true. It should have two distinct eigenvalues.
This each matrix?
No, this thing squared.
This thing squared.
Because you do it twice to take one around the other.
I see. So it's a rotation by
pi.
By pi, not by. So that I think explains this factor of 2.
Yes.
What is gives a reason why?
Yes, I think.
The matrix was 0, 1, minus 1, 0. The square of that is minus 1.
Yeah, so it's just so that's how many eigenvalues you have?
So
Just one, right? That's I'm still confused.
Sorry, what matrix are you talking about?
See this matrix R that David talked about?
Yeah.
Is the matrix that takes a state and tells you what state you get when you do this funny operation.
Yes.
Okay, so now I can do it twice.
Yeah, you're only going to get -1.
You're only
going to get minus.
minus 1. I thought this was the same in conformity theory. Maybe I'm making the dictionary wrong. As effectively taking one operator out. Maybe this is that. I can't. I'm not
So
sure.
this is the point, no? This is the even odd business. When you just have 2, you can't have a 1. You can't choose to 1.
What does that mean?
Like, it's basically. What is it? 0 and 1 are roughly the eigen, are whether there's a fermion in the fusion or not.
Is that what you're saying?
Yes, and then you can't have 1. You only look at 2
So if you had just two Majorana modes, you You can make one canonical fermion, and it's either
Zero
present or not.
with whether you have
So, can I ask a dumber question? If I take two Majorana poles and that I can think of as one complex fermion that's either there or not there. Now I do your swap. If it's there, and I do your swap if it's not there. Am I getting two different answers?
I don't understand. Maybe
I'm just saying
if I have
that
two Majorana modes, I've got a two-state system.
that's right.
Is that two-state system?
That's what I'm asking.
The two things that come from your fusion.
That's what I'm asking.
The 0 and the 1.
But in this language, where do I know that two-state system was occupied or not? I mean, where do I know that complex fermion was there or
It
not?
depends on which chiral spinor representation. So that makes it sound like the one you're after, the other half. The Hilbert space.
probably, but that's what.
That's what, yeah.
No, somehow to get a one, you need to have a third way playing a role in the argument. I don't see how it can, but maybe you need to play around two at the same time or something.
Well, no, you need another two which confuse to give another
That's what I'm saying, yeah.
that come together.
Yeah.
You need a third way to get the.
Of course, I had 4 vortices. I fused this and this to one, that and that to one. These two fused to situ. That's wrong.
What do you mean fuse
In
voltage?
fact, it's necessary to get the two-dimensional Hilbert space.
Yeah.
So it can't be the other.
Yeah, I think. No, yeah.
Yeah.
Wait, what do you mean by fusing the two voltages?
You see, the math is that these wave functions are one-to-one what I call conformal blocks of these operators.
Yes.
So conformal blocks are just the basis for the correlators.
Yeah.
Okay. So now let's say we've got 4 correlators.
Yes.
Okay. One way to think of the basis of correlators, correlators have to be in singlets of your group
Yeah.
because otherwise you get 0. So you can take this half and half,
Yeah.
and you can Klebsch-Corbin-Kappen to 0 and 1.
Yes.
You can Klebsch-Corbin-Kappen this guy to 0 and 1.
Okay.
Okay. And then
The one.
use the OP, the 1 and the 1 fuse, the 0 and the 0 fuse. That's one. It's a 2-dimensional basis. That's one 2-dimensional basis for this space. That would explain the 2, 4. Okay. So, but now if you couple this guy and that guy to a 0, you get one phase when you take one round the other. Just from the OP. Because you get 1 over Zi Z12 to the power delta 1 plus delta 2 minus delta product. Okay, and the phase will come from the deltas are just completely given.
What are the two phases that you put together as you take? How do you know they're different?
I know they're different because I know that the dimension of 1 and 0 are different. Unless that's wrong because k is so small. Right.
What are the dimensions?
I don't remember the formulas, I don't know, just assuming they're different. Suppose I have 1 and 2. Okay. So I'm fusing this to give a 3. Then I'm going to get 1 over Z12 to the power delta 1 plus delta 2 minus delta 3. Right? So delta 1 is what it is, it's the dimension of the spin half. Then delta 2 is what it is, so it's 2 delta half. And then the 2 options here, you can get either delta 0, which is 0, or delta 1, which I presume is non-zero. So that gives you 2 different phases. These should be just the. Of course, k is so small that it could be the. This problem. Okay.
Would be nice to figure out.
Yes.
Okay, any other questions? Alright, this is it for making up wave functions. We're taking a break next week, but when we return, we're going to do Chern-Simons theory. And we're just going to throw everything out that we've done so far. We're going to start from scratch and we're going to ask what possible effective theories could you have to describe any system between those combinations? And just from that simple question, we'll build up, we'll understand some properties of Chern-Simons theories and we'll see how you can reproduce a lot of the things we've seen. I'm not sure. Well, given that there's some interest in non-abelian Chern-Simons theories, maybe we should push forward and do that. I think given time limits, our choices are probably non-abelian Chern-Simons or the conformal field theory approach. Anyway, we can see what. Okay, see you in a week.